talking about our, I think it was this one. Oops, well, no, not that one. This one. It's this one. Oh, it's just an older version of it. Okay. All right, yeah, so last time we were talking about the jump instruction. Okay, so let's look back at our table of operations here, right? So the thing that makes this thing really a computer is the fact that we can make a conditional decision, um, namely the second to last instruction on the list there, right? So if a register's value of our choosing is equal to the contents of register 0, then we can jump to a different place in memory and start executing the code that we find there. If the two things are not, or sorry, if the register is the same as register 0, I said different. If the register's contents are different, then we just move on to the next instruction in the list, okay? And so this allows us to do things like an if-then kind of statement, right? Or an if-then-else kind of statement. So what would something like that have looked like, an if-then-else statement, if we had written in Python? All right, let me close all the stuff from my other class. Right, so in Python or something, I might have written like, let's say num is 0, and then I could do, oh, I don't know, if num is greater than 5, print greater, else print not greater. Something like that. I'm just making something up, right? So what do we do here, right? If num is greater than 5, well, num is greater than 5 is a Boolean thing. It's either true or it's not, right? And if that statement is true, we do whatever's on the if in the if part, and otherwise we do whatever's in the else part, right? So the code would jump to a different place to execute. It would sort of skip over whatever's inside the if part, okay? Which right now is just one line, but it could be, you know, like 500 or something, right? Okay, so so there's a couple of questions that we have to ask here, right? One is, did you get them? Yeah. Excellent, thank you. One is, we can only do the comparison between a register, I'll just throw them on the table there, I'll give them out at the end, between a register and register 0, okay? So last week or earlier this week when we were working on this stuff, this is why I kind of said don't use register 0, because you have to use it for this, these conditional expressions, okay? Yeah, so don't use register 0 except for this purpose, because you have to use it for this purpose, and this way you won't confuse yourself later. Okay, the second thing that we have to do is we have to realize that, so like this statement here, number greater than 5. What does it mean for a number to be greater than 5? I'm sorry? Yeah, right, it's more than 5. I know it's kind of a stupid question when I say it that way. Okay, but so here's the real question though. If our computer can only determine whether or not two things are equal, and we've got a statement here that's greater than, we have to translate the concept of being greater than 5 into a concept of being equal to or not equal to something. Okay, so do you see the issue? We'll have to figure out how to solve it. Okay, so this is the fun part. Okay, okay. So let me just, for sake of initial demonstration, do something that's not something like that. All right, I could do if num equals 5, right? Okay, so if I wanted to compare a number to the number 5, I have to put our number someplace, and I need to put the number 5 inside uh, register 0, okay? All right, so let's go to, let's see which example I want to do first. Okay, so, yeah, so let's just write an example here. So let me put this on the left of the screen, and hopefully it'll fit nicely. So I wonder if the new Debian version of Pi OS has the window snap feature like Windows does, because that is pretty freaking handy. Okay, so let's write something like this, but write it in our assembly language. Okay. All right. So first off, I need to put the number that I'm comparing into a register someplace. All right, and for sake of demonstration, let's just pick that number in advance. So let me load register 1 with the bit pattern. Well, let me start with 5. Okay. And then I need to load register 0 with the thing that I want to compare with. So actually, let me change this one to 6 for right now. Okay. So I'm putting the thing I want to compare to, right? So the 5 of the equal to statement, that's what goes in register 0. The number that I wish to compare to it goes in register, well, whichever one I want. I'm just going to use 1 for sake of demonstration. Okay. Okay. Now, the other thing is, do I have a print statement here on this computer? There's no way to print data. There's no screen or anything like that. Okay, so how could I output something instead of printing? Yeah. Yeah, I could store it to someplace in memory. Okay. And let me say, and I'm just going to make this up, that if it's greater, I'll store, actually, let me just do this. If it's greater, I'll store a 1 in memory someplace. And if it's not, I'll store a 0 in memory someplace. Okay. Just as sort of because we can't actually print numbers because there's no screen on this thing. Okay, is that all right? We? No. We? No? We? Okay. All right. So, so at this point, all right, let me put the line numbers in, or the memory addresses in. At this point, I'm ready to do a comparison between the two registers, okay? And the syntax for the comparison is jump register we're comparing to, memory address to jump to. Okay, so here's the thing. Do I know where in memory I want to jump? Not yet. I do know what instructions I want to jump to, or I will once I've written them. Okay, but I don't know where in memory I'm going to go to just yet. So let's put, you see how I have XY there as kind of a placeholder? Let me leave that placeholder in, and we'll go back and replace it with what it needs to be once we've finished a few other things. Okay, is that all right? Okay, So which register do I want to compare to register 0? In this case, register 1. So I'm going to jump, and I'm going to do register 1, and I'm going to go to memory address XY. I don't know where XY is yet. Okay? But we will figure that out. Okay, so if the register 0 and register 1 are equal to each other, the jump does take place. So it takes place on equality. Okay, what do we want to do if the jump does not take place? Okay, that would be the else case. What were we going to do in the else case? Store 0, the number 0 someplace. Okay, so let me just store the number 0. Okay, well, first off, do I have the number 0 in memory anywhere? No. So what do I have to do first? I have to load it, and I don't want to use register 1 or 0 because they've already been kind of used for something else. So let me use register 2. Okay, and then I need to store this to some place in memory. And I'm just going to arbitrarily choose to put it in the very, very last memory cell for sake of demonstration. But I could put it anywhere I want it, right? Okay, is that okay? Yes. Instead of, so 00 is a number. It's also a bit, so 00 is in hex, right? Right, so what is 00 hex? That's really 8 zeros in binary. Yeah. So I guess maybe I'm not understanding your question. Mm, okay, I see. Because what is the difference between hashtag and dollar sign? And the dollar sign is whatever is in that memory address. Okay, so let me rephrase the difference between the dollar sign and the hashtag. Okay. All right, so basement of Sparks. There's a crap ton of mailboxes. They all have numbers on them, right? So imagine that we have 256 mailboxes, and they all have a label on the front of them, 00 through FF, right? So they're all addressed in hexadecimal, okay? Dollar sign, if I want to load from dollar sign 00, what that's doing is going to mailbox 00, opening it, and whatever data is inside is what actually goes into the register. Okay, but whatever's data is inside, you would agree, is not necessarily the same as what the number on the front of the box is, right? That's the difference. Okay, so yeah, so if I load from memory, I go out to the memory address I've specified, and whatever's there is what I load in. Okay, in which a lot of times we want that. Not here, because I here want the specific number 0, because I picked that number out of, just for sake of example, but I wanted that number, okay? And so that's why I put the hash mark instead of the dollar sign. Okay, so does that make sense? Yeah? All right, the next instruction though, because that one does have a dollar sign, the store, what that's saying is I've got a number in register 2. Okay, it happens to be 00, but there's a number in register 2. Take that number and go out to memory cell FF, open the door, and put that data in and shut the door. Okay, so do we see the distinction here? Question, Mr. Cook? Mm-hmm. Yeah, it'd be like as if the mailman had like 16 hands, right? Okay, this is where obviously the analogy breaks down. Okay, Or maybe better put, the mailman has a desk with sort of 16 little slots on it. You guys know, like those office sorters where you've got like an inbox and outbox kind of thing, right? He's got one of those with sort of 16 little slots, and then sitting behind him is a giant wall of mailboxes. So he can go out to the mailboxes and grab data and put it on his desk and then do stuff with it on his desk. And when he wants to put it back into memory, he picks it up and goes and opens the door, and in the memory, in it goes. Okay. So this actually reminds me, this sort of analogy. There was a book. Let me see if I can find it real quick. Um, I think it was called Osborne. Yeah, here it is. Usborne, excuse me. Okay, so this is this. Okay, so it was Usborne Assembly 6502. Here we go. There we are. Okay. All right, so let me show you guys this book because it's really, really quite cool. Oh, look, I get to ban somebody on Twitch. All right, so let's report spam. Okay, they're banned. Um, oh, I don't want to sign in. Dang it. Okay, I'm not going to sign in. We don't have time for that. But anyway, there was this series of books meant for kids in the 80s, and one of them actually is assembly language programming for computers of the era. Okay, so there were sort of um, two processors that were very common in basically every home or school computer that you would likely be able to get your hands on back then. The 6502, which powered the Commodore 64, the Apple II, the 8-bit Nintendo, a bunch of Atari's computers, the Atari video game consoles, right? Like all of these things. And then also there was another processor called the Z80 uh, that was actually developed by a couple of engineers that left Intel and founded their own company and then started developing their own stuff. Uh, and one computer that used that was the TRS-80, Tandy Radio Shack 80, or more affectionately known as the Trash 80, because the quality control was a little shoddy. Um, anyway, but I'll get the PDF of this and put it up on Canvas, and I think you guys will like it because um, it sort of is like if you want to move something from a register to memory, it's like there's this little knight in armor, and he carries the data from one place to the other, and it's yeah, it's cute. Okay, anyway, so right, so that's the difference between $sign and hash mark, and hopefully that clears that up, right? Okay, so I'm going to store the 0 to memory someplace, and then I'll just halt. I'm finished. Okay. Now, what do we do if the number? Okay, so this is sort of the irony of this. In Python, okay, and then for that matter, most languages, what order did we write the statements in? We wrote the true part first and the false part second. Ironically, in this case, we're actually doing the exact opposite. We're writing the else part first and the other part second. It's kind of weird, okay? But the reason is because if the jump does not take place, that's the false case, and we just move on to the next line of code, as opposed to jumping to some other place in the code. Okay, so I know that seems a little backwards, and it in some senses kind of is, but this is the limitation of this architecture. Okay, so we have our instruction jumps only on equality. Okay, only when two things are equal, and it doesn't jump otherwise. Now, real processor architectures have more jump instructions. So they have jump on not equal, or jump on greater than, or jump on less than or equal to, or whatever, right? So there's a richer variety of these things that you have at your disposal in a real architecture. But they're all there more for convenience than they are for necessity, because you can translate the idea of less than, and I'll show you guys how to do this, into a question about equality. It's a complicated translation, but it can be done, okay? So, all right, so are we cool with that? The stuff I've got highlighted is the else case, basically. Oui ou non? Okay, so now we just got to write the true case where we were going to store the number 1 to a place in memory, and let's see what that looks like. All right, so it'll be very similar, to what I have highlighted. I need to load the number 01 this time so that I can store it in memory cell FF, and I'm just using the very last mailbox as sort of my output location. Yeah. I actually only stored ever once, okay? And I'll come back to that in just a second, okay? Okay, so this block of code and this block of code, only one of them will ever actually run for a given instance of running the program, okay? So does it look like I'm putting two numbers in the same register or two different things out into the same memory address? It looks like it, okay, but only one of those two blocks of code will ever actually get executed, in the same way that in the Python up above, is if I were to run that Python program, would it both print greater and not greater? Would that ever happen? No, because the number that I defined is either equal to 0 or it isn't. There's no, it's both. You can't both be equal and not equal, right? That's Shakespeare, right? To be or not to be. Yeah? Or you could do it in Klingon. Tach, pach, tach, bet. No? You guys aren't up on your Klingon? Huh? Yeah, well, Cody, where's Cody? Well, let's get a picture, shall we? Huh? Oh, sure. Hmm. Anybody else want to shame one of their friends? No, we good? Okay. All right, so we're almost finished. Okay, what's the one thing we have to go back and finish? The jump. Okay, well, two things, but this thing here, I put a placeholder in, right? This needs to be a memory address for where we jump to. Where do we go for the printing 01 case? We go to these instructions that start here. Where do they start? Memory cell 0C. So what do I need to change XY to? 0C, so it points to that. Okay, so is that okay? Okay, so that's the only change we needed to do by going sort of back and fixing the placeholders. Okay. Okay, now the last thing we need to do is we need to translate all of our instructions into this stuff, right? So that we can put it in our little simulator and actually run the thing. Is that okay? Okay, so let's do that. What is load 1 and the number 06? Which opcode? 2. Which register? What number? Okay. What about this one? Okay. B10C for the jump. B is jump. 1 is the register we're looking at. 0C is the place you jump to if you jump. Okay, and then we just need to continue this. So this would be 2200, 32FF, C000, 2201, 32FF, C000. Okay, so again, you did not have to memorize all of those. I will always give you this table, okay? However, I think that you guys will notice that after you program and are writing some stuff, you'll start to kind of memorize at least a little bit of it by osmosis, right? If you have to look up something 50 times, eventually it's just going to stick, okay? Okay, so there's our program. And what's the last thing I need to do? I just need to put all of this stuff in all in one string so that I can copy it and we can go out and put it in Joel's emulator. Okay, good? All right, so let's go over here. Okay, and then remember, put a hash mark, paste in the stuff, hit enter, and then refresh the page. And there's all of our stuff in memory. Okay, so now we can run it. Okay, so watch the execution, the program flow. Okay, so it's finished. What's sitting out there in memory cell FF? Because last time I checked, 5 and 6 were not the same number. Okay. If I change the number 6 here to the number 5, okay, so let me just make that little tweak, okay, and rerun it, then what should we end up seeing this time? There we go. Okay. All right. So that gives us the ability to make decisions, right? Now, last time, for sake of demonstration, we also made an unconditional jump, right? So we had a jump that always took place. And what was the trick for that? Which register did we compare to register 0? It's almost a trick question. Register 0, okay? Because what the jump instruction is doing is saying, is register 0 equal to the register you've told me to look at? Yes or no? Well, if I compare register 0 to itself, last time I checked, those two things are going to be the same no matter what. So That's an unconditional jump. It always takes place, okay? And so if we think about like a for loop or a while loop or something, like what's the structure of a while loop? While condition, do stuff, right? Okay, and then presumably when you're doing stuff that might change the value of the condition, because otherwise it's an endless loop. And in our case, what we're really doing, if we wanted to make a while loop, it'd be like if condition true, exit loop. And we do stuff. And then down here we'd say go back to start of loop, right? So we check it, do stuff, go back. Check it, do stuff, go back. And this go back is an unconditional jump. Just takes us right back up to where we check the condition again, and if the condition's satisfied or not satisfied, we do or do not do stuff as accordingly, and so we could build loops out of this too. Okay, but it all comes down to uses of the jump instruction. Okay, now let me actually return to. At first, I made the example checking whether or not, like the Python example, not the assembly one, if a number was greater than 5. Okay, we said, well, wait a minute, we got a problem because how do you check if something's greater than 5 if all you can check is if two things are the same? That's a problem, right? Okay, let me change the question. Is it possible for me to check whether or not a number is positive or negative? Well, not directly, okay? But if we think about 2's complement and binary encodings, right? How do we know if I gave you an 8-bit number, just wrote it down, how would you know instantly if that was a positive or a negative number? The sign bit, okay? Because if the sign bit is a 1, what does that tell you? The number is negative, and if it's a 0, then it tells you that the number is or possibly 0, right? But it tells you it's greater than or equal to 0, okay? So I can, if we can figure out how to deal with this sign bit, I can tell whether or not something is less than 0 or greater than or equal to 0. Wow, now we're going somewhere, okay? So let me write down here on the board just a random negative number. Okay, and I don't really care what this number is for this purposes, but is it clear that it's negative? Okay, and how do I know that that number is negative? Because the starting bit is a 1, okay? And so as an int 8, which every integer on this machine is an int 8, there's no distinction, okay? Then we know it's negative, okay? Now, so which bit is it that I really care about? The first bit, or really the last bit, I guess, right? The far left-hand bit. Do I care about what any of the other stuff is? No. Okay. So what I'm going to do is I'm going to do a trick. Which bit position or positions do I care about? Just this one. So I'll put a 1 in a number in that position. Do I care about any of the other 7 bits? No. So I'm going to put zeros in the positions I don't care about. Okay, so this is a second number. I've got the original number and I've got this number that I've cleverly chosen. You'll see why it's clever in a second. Okay, and I'm going to do something with those two numbers. Well, what somethings do I have at my disposal on this architecture? I could add those numbers. That's not particularly useful. What else can I do with two numbers? What other instructions do I have? Okay, definitely not storing or loading. That's not going to help here. Adding isn't going to help, but what else might I use? I could do some rotations. Not in this case will that be useful, but I could. What other operations have I? I do not have subtraction. Okay, not as a single instruction, right? I do have subtraction because we know how to do two's complement and stuff like that. But actually, okay, on that subject, what was the trick for subtraction? Flipping the bits, right? How did we flip the bits on the computer thing here? We XORed them against a pattern of all ones, right? So we did the old Texas two-step. We had a cleverly selected bit pattern and the appropriately chosen Boolean operation. And the combination of those two things, I reckon, solved our problems. What do you guys think of my accent? It's something? Oklahoma? I almost said that the same way as like New York City. Okay. How many of you guys have seen those commercials, like for the Pace salsa? So in the 90s, before we had DVRs, we had AVRs. They were called VHS recorders. But yeah, it was dark times, man. Um, anyway, so when you watch TV live, because there was no such thing as streaming or DVRs or anything like that, you had to sit through the commercials. And fortunately, some of them were really funny. But Pace, you know, company that makes salsa, right? It's a pretty good salsa. Not as good as making it yourself, but for store bought, it's pretty good. Um, had these commercials of like Texas cattle drivers, you know, on the cattle lines, driving cattle from Texas up to Chicago to the processing plants, right? And they'd be out in the middle of nowhere, and the chuck wagon would be whatever, and it's dark, and a fire is roaring, and then the cook is like, brings out this salsa, and uh, you know, somebody's like, "What is this? This is awful." And he shows him the jar, and he says, "This stuff was made in New York City." And all the other cowboys are like, "New York City?" And then they brand the cook with like a Texas logo or whatever as punishment for having this awful salsa. I know it's much funnier if you watch it. And okay, yeah, you kids these days. Okay, anyway, so the Texas two-step, right, is cleverly selected bit pattern combined with cleverly chosen logical or Boolean operation. In this case, the cleverly selected number is 1 followed by all zeros. The Boolean operation that I'm choosing to do is AND. Okay, now, because I put zeros in these 7 positions, what am I guaranteed to get for the last 7 spots in the answer? Because remember, this goes bitwise, right? What do I get? A bunch of zeros, okay? Because anything ANDed with 0 is 0, right? So those 7 are easy. What about the 8th bit? In this example, what is it? It's a 1, okay? So ANDing against, what is this number, by the way, in hex? Hmm? As an int 8, not an uint 8. Well, that's its value, right? But as in hex, what is it? 80, right? Okay. If I AND it against the number 80, I get either I get precisely one of those two answers. Either I get 00, And that occurs when the first, the sign bit was 0, or I get 8-0, and that occurs when the sign bit was a 1. Well, it's one or the other. So can I check whether or not it's, so if I and a number against this pattern, can I check if that's the same as 0-0 or 8-0? Yes. Now I've got a way to check whether or not a number is negative, okay, by comparing it to 8-0 after you and it against 8-0. Okay, does that kind of make sense? Ah, all right. So for my next trick, how do I tell if a number is bigger than 5? Well, what does it mean for a number to be bigger than 5? Okay, this is almost a stupid question because you guys are looking at me thinking, well, Dr. McKinney, if you really want us to know, if you don't know what it means to be bigger than 5, how the hell did you get a PhD in mathematics? Or better put, how the hell did you get out of elementary school? Okay, so I promise this is not a stupid question. What's another way to ask this question that's a different question but equivalent in terms of its answer? Okay. Uh, yes. Okay, but how are you going to tell that to the computer, right? So that's the other question, right? Like, yes, you could tell your kid brother or something. Well, if it's bigger than 5, if you need a second hand to count it, that's true. But tell that to your kid brother little computer here. Okay, once I write this on the board, you guys are going to be like, well, oh, of course. N greater than 5 means that n minus 5 is greater than 0. And if only we had just figured out a way to check whether or not numbers are bigger than or less than 0. Ah, and if only we had a way of doing subtraction. Did we do that last time? Yeah, it's almost like we have to like put together two pieces that we've learned and combine them in a new way to get something more complex and more interesting. Like, no? You guys not having it? Do you guys agree that those two things are equivalent mathematical statements? Yeah. The second one is easier to work with in the computer context because we've just determined how we can compare numbers to see if they're bigger than, less than, or equal to 0. Okay, so we have to change the question into something that we can answer appropriately with the computer. Now this means, like, and this is the thing about something like Python or C or Java, right? In Python, you just type if n is greater than 5, okay? And the computer, or the compiler or whatever, just sorts all the details out for you. But in assembly, you have none of those tools. You have to build it all yourself. Okay, so this would be like, I don't know, has anybody played like Valheim or, well, actually Minecraft, I guess would be a good example, right? Or any of these games where you like find yourself in a world with nothing but like a simple tool, and then you have to like go find stuff and craft bigger things and better tools and whatever. And that's the game loop, right? Minecraft is certainly a great example of it. Well, that's kind of like what we've got, right? We only have these 12 tools at our disposal, and we have to combine them in clever ways in order to do complex operations. And as Owen can attest, you can do some pretty complex operations with a simple pile of basic ones. Yeah, so anyway. Now, how many of you guys looking at this sort of assembly stuff think, oh my God, this is the worst thing ever. I hate my life right now. Yeah? Okay. How many of you guys want to be CS majors or minors? Well, I hope you like this stuff because guess what you're going to be doing for an entire semester in CS241? Yes, but with a real architecture that has a few bit more than 12 instructions. Okay. But you remember all these examples that like I'm like, oh, let me close this for my other class. That's what the other class is doing. And right now you're just like, right? But yeah, okay. All right. So you CS majors and minors better develop a taste for this, even if it's like, I don't really like wine, but I'll drink a glass on Thanksgiving and Christmas, kind of thing. Okay. All right. Well, I've waxed poetic enough. It's time for a break. Don't leave without me giving you your exam back. And what is the procedure for retakes aujourd'hui? Same thing as last week. Just come by my office. Okay? All right. See you guys on Monday.